In this video, I'll show you how to use GeoGebra.org to do a one sample confidence interval for a sample proportion. So go to the website geogebra.org/classic #probability. There's two tabs, distribution and statistics. This time we'll be on the statistics tab. Below that is a drop down for all the different tests and confidence intervals that you can do on GeoGebra, which is pretty thorough. We are going to focus on the second grouping of tests, which is actually the confidence intervals. So go to Z estimate of a proportion. There's only a few things that you need to be able to do a confidence interval on GeoGebra. You need to know the confidence level, you need to know the number of successes, and the sample size. So with just those three facts, you'll be able to get your confidence interval and summary statistics, which is going to show up on the bottom half of the graph. I already have an example that I'm going to borrow from the Open Intro Statistics Advanced High School Statistics. It's on page 303. The Gallup organization began measuring the public's view of the Supreme Court's job performance in 2000 and measured it every year since then with questions. Do you approve or disapprove of the way the Supreme Court is handling its job? In 2018, the Gallup poll randomly sampled 1,033 adults in the U.S. and found that 53% of them approved. We know that 53% is just a point estimate because it's only from one sample instead of taking lots and lots of samples. We also know that the samples will vary. The sample statistics will vary from sample to sample. So the confidence interval is going to give us a range of likely values that we might see as a sample proportion and thus estimating the population proportion. So what we need to do is identify our sample size, number of successes, and confidence level. So as you work through or read through these pages, down near the end is the actual math for constructing a 90% confidence interval for P, the population proportion of all U.S. adults that approve of the job the Supreme Court is doing. So down below here is a really generic way to write out a confidence interval, and it's really useful because it applies to any estimate that you can compute. You take the point estimate plus or minus a critical value times the standard error of the estimate. So in our case, our point estimate is a sample proportion, so a p-hat value, plus or minus. A critical value is going to be a z-value. That's because the sampling distribution for a proportion follows a normal distribution. So we're going to be getting our z-values from the normal table, or in our case, when we use GeoGebra, it's computed automatically. We don't even see the math of coming up with a critical value. And then the standard error of the estimate. So this is all to work by hand. Let's plug in what we know. Here's our confidence interval. We have point estimate plus or minus z star, or maybe z asterisk, times the standard error of the estimate. So our point estimate is 0.43, and then plus or minus 1.65. So where did this number come from? This is a special z-value, we call maybe z star, that puts 90% of the area between negative 1.65 and positive 1.65. So it's not just going to the normal distribution and saying, I need 90% of the data in the left tail, what's z? We need to know 90% in the middle of the distribution. So that puts 5% of the area in each tail. So if you were using a normal distribution, you'd want to look up what z-value puts 5% area to the left, and then just kind of ignore the negative sign. Or think about it as 90 is in the middle, 5% is on the right. So what z-value puts 95% area to the entire left side of the distribution? And that's how you'll see that 1.65 is the answer. You might also consider you're using 1.645 or 1.64. It sort of varies from book to book and depending on how many decimal places you want to use. This book uses 2 decimal places. Okay, so back to our formula. We have the point estimate. We now understand what z is. The standard error of the estimate, that is the formula p hat times 1 minus p hat divided by n, and then take the square root. So that's also the standard deviation of the sampling distribution for proportion. You've probably seen that. So since we don't know a population proportion, we put in our sample proportion, 0.53, into the formula and get 0.016. That's rounded out to 3 decimal places. If you can round out to more, you'll probably get a more accurate answer in the end. So then to actually get your confidence interval, first you multiply z times the standard error, get an answer, and then subtract that number from 0.53, there's your lower bound, add that number to 0.53, there's your upper bound. So the way we interpret this interval is we are 90% confident that the true proportion of U.S. adults who approve of the job the Supreme Court is doing is between 0.504 and 0.556. So to break down the sentence, what we're doing is we are saying we are blank % confident, so insert your confidence level here, that the true proportion, this is referring to the population because the population is the true amount of people and then its proportion, so the true proportion, and the next part comes from the description of the question. Of U.S. adults who approve of the job that the Supreme Court is doing is, and then you fill in the 2 endpoints of your interval between lower endpoint and upper endpoint. These are written as decimals, but it's also okay to write your answers as percents. For example, 50.4% and 55.6%. All right, now let's go to GeoGebra and have it do the math for us. So what we need from GeoGebra is our confidence level. And that was 0.90 from the original question. I'm going to fill in n first. So that was 1033. That's how many people were surveyed. The next part is something we didn't directly have. They didn't tell us how many people said that they support the job that the Supreme Court is doing. We just know that 53% of the sample size says yes. So what we'll do is do a little bit of math. So we need to go to your calculator and we're going to take 0.53 times sample size. So 53% of the sample size yields 547.49 people. So I'll literally write 547.49. Now, we didn't actually sample a fraction of a person. It was whole numbers of people that were sampled. So what's likely true is that in reality, 547 people said that they support the job, and the 53% was actually just an estimate. Maybe it was 52.9 and they rounded it to 53 just to be nice. Or maybe it was 53.3 and they rounded down to 53. Either way, we don't have all of the data, so we're just going to do the best we can. So I'm going to keep the number of successes 547.49. And once I type in that number, the results are put out for me right here. It tells me that I did a z estimate of a proportion with this many successes out of a sample size down below. Here's the standard error, which is a little bit off than the book was showing because, again, we had to make some adjustments for sample size. The lower limit and upper limit are also pretty close. They also go out to 4 decimal places instead. But you can see that just that tiny little bit of error was simply just from rounding error. And then here's another way to write our interval, 0.53 plus or minus 0.0255. So there's a couple ways to write your intervals. One isn't wrong, one isn't right. They're just different ways of showing the results. So there you go. That's how you can use GeoGebra to do a 1 sample confidence interval for a proportion.